So this is our last lesson of the unit, and this is connecting another topic to the normal distribution. But you're going to see, ultimately, it's a kind of directly is connected, but it ends up being somewhat loose in terms of how you're going to use. Yeah, this is the last one. So what it connects to is something we haven't seen in a long time, and that's this thing, which is called the binomial expansion or binomial probability. And you may recall this, you may not, but some probability events can fit into a category where they fit this. Namely, if you were to have two possible outcomes. So remember if you had success versus failure. So like flipping a coin, you can term as success versus failure. Even if you're rolling a die, even though there's 6 outcomes on a die, you could say, okay, what's my probability of rolling a 2 10 times out of 20? So it would be, a success would be rolling the 2, and rolling everything else would be failure. So in this is the binomial, where n is do you remember what n is?
Number, chosen successes? Or?
Yeah, well, number of trials, close. So this is the number of trials. P is always probability of success, so whatever you deem success. And I'm going to change this k to an x.
Is that all probability?
K is, or x, if we change this to x, because we called it x before, but I think I put in k because the textbook does it, but it's the number of successes. So if I flip a coin 20 times and I want 10 heads, x would be 10. So that would be the number of successes. And how this is going to connect to what we were doing with the normal distribution, you'll see in a minute. But just to remind you how this might work, we did things like this. This is very much a review of what we did a long time ago. Find the probability of flipping 20 heads in 50 trials. So in this scenario, n would be what? Yeah, 50 is my number of trials, perfect. P is my probability of success. Flipping a coin, unless it's been weighted, is what's the probability of one head?
1/2.
Yeah, 1/2 or 0.5, exactly. So you'd use 1/2. And then X would be the number of successes in this situation, which would be 20. So this is a specific, what's the probability that you flip exactly 20 out of 50 times, right? So imagine, how many would you expect to flip heads in 50? 25, exactly. So we're saying just if we flip 20, so the probability is probably going to be pretty small, so we would say the probability that X is equal to 20, exactly. And we would plug this in, and we actually use something on our calculator called the binom PDF, and we're going to get to that in a second, but let's just do it this way. So you would have 50 choose 20. Remember, this is that n choose C, or n choose R rather, with choosing not permutations, but combinations. So n choose R. And then you would have 0.5 to the number of successes. So it's like you have 20 heads, and then you would have the equivalent, and tails is just going to be 1 minus the probability of success, so 1 minus 0.5. And that leaves, how many tails would you have? Yeah, 50, or out of the 50, you would have 30. So you take 50 minus 20 gives you 30. And you would plug this in, and you would get approximately 0.042. So this is the probability that you would get exactly 20. This situation, if you think about what this variable is this a discrete variable or a continuous variable? So flipping a coin and getting heads, is that continuous or discrete? Yeah, it's discrete, exactly. You can only get whole numbers. A binomial is often when you have whole numbers. So this is often used with discrete data.
Are we going to have all of these formulas on the test?
You will, yeah. Everything we've been doing with the normal distribution to this point has not been discrete data. There was one question in the homework a couple classes ago that talked about number of hot dogs or something. that would be discrete, but it actually recognizes it. Most of the time we're talking about the heights and things like that, length and time. We use the binomial when you have discrete data and you know that there are multiple trials. And the trials have to be identical. And what that means is that the probability doesn't change. So like if I toss a head, the 10th time my probability of a head is the same as the first time. It doesn't change. So the probability of each trial is independent. And all that means is it doesn't change. It doesn't affect the next one. And the last point is just that there are two possible outcomes. So deemed often success and failure. So there are two outcomes. Success and failure. And you don't necessarily have to label them that way, but that's often how it's described. So there are many situations, like if you guessed on a multiple choice test and you're like, what's my chance of passing or getting 2 out of 10 if I guess on all 10 multiple choice questions? That's the situation with a binomial. Anytime you have something where something might pass or might not pass, that means you probably have a binomial. How this relates to the normal distribution is the next question. It says, find the probability of tossing less than 20 tails in 50 trials. So if you flipped a coin, what's the probability that you get less than 20? Think about that for a second.
It's lower than if you.
Yeah, it would be less than 20, but that means you could get how many heads? 0, 1, 2, 3, all the way to 19. Which would mean you would have to do something like this, where you go the probability of x equals 0 plus the probability that x equals 1, and clearly we're not going to do that because there's an easier way. And this is where it relates to the normal distribution. And I just want to show you this thing. I've kind of shown you something similar before, but let's just take a look at this one. Remember I said they actually figured out the normal distribution. Let's see if I can get this up. The normal distribution probabilities they figured out by flipping coins. And so they didn't go out and measure thousands and thousands of people and find that they fit the normal. They actually flipped coins to do this. So if I was to increase the number of trials, let's say I increase it to 50. Look what happens to the distribution. This is exactly flipping coins. So my probability of success is 0.5. My probability or my number of trials is 50. Like we said before, I think Oscar said it, the number that you would expect to get would be 25. This fits perfectly to a normal distribution. But is it a curve that goes over? No. There's all these gaps in it because it's discrete data. It's not continuous data, right? You can't have, exactly, you don't have any numbers between all of those whole numbers. So as a result, you don't have a perfect bell curve. And so it changes it ever so slightly and you have to make some accommodations. The nice thing is your calculator is going to do almost all of that for you. But notice, if I just go back for a quick second, if I look at this, if I reduce the number of trials, like let's say I make it 5, and I take a look at this, it really doesn't even look like the normal distribution, right? There is a minimum number of trials that you need in order to get to what is acceptable to fit the normal distribution. And that number happens to be the number of trials times the probability of success. And that number needs to be greater than 5. So I'm going to write that down here. So if you have a discrete data situation that's dealing with a binomial, you can use the normal distribution, but you have to check to make sure that n times the probability of success is greater than 5. And because probability of success can be 1 minus p or just p, we have to say it's the same thing. This also needs to be greater than 5. This is a general rule. in stats that you say a lot of things have to be greater than 5. Statistically, it works out somewhat well in order to do this. So these are the tests that you would have to check to make sure that your binomial fits the normal distribution. So if the two conditions are met, then the binomial,
So n is the number of trials and p is the percent chance of what? Of success?
exactly.
If those things are greater than 5 and n times 1 minus p. What is that again? What is 1 minus p representing?
It's really just the probability of failure. So if you are tossing coins, it doesn't matter because p is the same as 1 minus p, right?
Yeah.
Head is the same as a tail, but if you had something else like tossing a die and you're looking at the number of 2s on a die, the probability of getting 1 2 is 1/6, and therefore the probability of failure is 5 out of 6. Yeah. So we're going to use this, and hopefully this will all come a bit clearer as we go through, but the closer p is to 0 or 1, so if it's really small or really big, close to 1, the more trials are required to fit the normal curve. And this is kind of what we do. We superimpose the normal distribution like this over top of this bar graph. And so it allows us to use something really similar, where in the middle is still my mean. And then if you go standard deviations above and below, you still have all of the same information that we saw from the normal distribution. So sometimes we will need to calculate the mean and the standard deviation of a normal distribution or of a binomial distribution to fit the normal distribution. In order to do that, we need formulas. Remember I said the mean, which is the middle of the graph, will always just be the number of trials times the probability of success. The standard deviation is a bit less obvious, but it takes the square root of that number and then multiplies it by the probability of failure, which is 1 minus p. These, again, are formulas that are given to you, but these are the formulas for binomial distribution. So you will use these in order to find the mean and standard deviation of those two things. This happens also to be, you've seen this before, you may not remember it, but this is also the expected value. So when I said, what's your expected number of heads if you toss the coin 50 times, you said you would expect to get 25. That also is the average. And like before, you can still use z-scores to solve these things, but we are also going to use what's called the binom CDF function. But just to remind you, z is just x minus the mean over the standard deviation. That's why you need the mean and the standard deviation of the binomial if you use the z-score. Okay, let's put this all together and try a couple questions. Good on that stuff?
Yes. Sure.
Okay, so we'll go back to that example we had with tossing the coin 50 times. It says, you toss the coin 50 times, what's the probability that you will get tails less than 20 times? So we want to use something in order to figure this out quicker. So n is our total number of trials. We said that's 50. Our p will be 0.5, so the probability of 1 head. Our mean is just a calculation. This is the n times p. So I'm going to take 50 times 0.5. So my average that I should look at is going to be 25. That's also the expected value. My standard deviation is going to be n times p times 1 minus p, which we had above. And I just throw that stuff in. So n times p was 25, and then I times that by 1 minus p. So I end up with, I'll just take the square root of that, approximately 3.54. I want to show you how to do this using the z-score, but ultimately you're going to use your calculator to try to figure this out. The z-score, if I wanted the probability that x is less than 20, if it's less than 20, do I include 20 in the calculation? No. So what you do is you actually sub in 1/2 of a number less than that. And you can use this, but you're probably gonna choose not to because you can use your calculator. So what you want is to use the z-score, if you choose to use the z-score, where you sub in that point that's slightly less than 20. This is the part that compensates for the fact that this is a binomial and not just a regular continuous graph. Minus the mean, which we said was 25, divided by the standard deviation, which is 3.54. And so that gives us approximately negative 1.55 as a z-score. This, like we did with the normal distribution, I would then go to my table. So here's negative 1.5, and I would scroll over to the other 0.5 rather, and this gets me a value of 0.0606. This would be the probability that you would get less than 20, in this case we said tails, I think it was heads before, but tails in 50 flips. What you probably would prefer to use is something a bit quicker. So if you pull out your calculator, if you have it, and you can do this on your iPad as well. If you go to, and all these instructions are here, through the same place where we went to the normal distribution. You got this, Robbie or Noah? Calculator?
Yes.
So go to second function vars. And remember here we had normal, CDF, and inverse normal. We used those. If you continue to scroll down, you also will find what's binom CDF. What does the C represent? Do you remember? It was the same C as in the normal one. Sometimes knowing what the C is versus P is helpful to actually know which one to use.
Combination?
Close, it's cumulative. So what we're doing is getting the cumulative probabilities from 0 through 19. So the C indicates that I'm going to use a cumulative one. On this calculator, it's slightly different than, say, yours, Noah, or yours, Lindsay. Yours is nicer. Yours is easier to do, which is great. On this calculator, I have to type in, yours will ask you what's the number of trials. So here I'm going to put 50, and then I have to put comma. What's my probability of success? 0.5. And then what's my x value? Because it's less than 20, I put 19. So what this is going to do is calculate all of the binomials from 0 through to 19. And you press enter, and we should get a number that's really close to what we had from the z-score table. This is actually, in fact, more accurate than what is in the z-score table. So I would write binom CDF bracket 50, comma 0.5, comma 19, and I get 0.0595 approximately. And I would accept either of those two answers. Obviously, the calculator version is way less work, and it's really just knowing how to use that and interpret your answer, which is nice. Any questions on the calculator part? Did you get it, Noah?
Oh, yeah.
Yeah, that's good. So let's try the next one then. We'll try a couple just to make sure it works all right. It says, what's the probability that you toss 20 or more tails? So this question is going to cause, on your calculator, it only goes from the left up to a point, right? So you can go from 0 to 20 or 0 to 19.
Subtract this from 1.
Exactly. You've got to then, if you're saying more than a certain number, so if I want the probability that x is 20 or more, so this is greater than or equal to 20, I want to take 1 minus the probability that x is less than or equal to 19. So when I see more, I always am going to have to put this 1 minus part. Your calculator will not compensate and do this differently.
That's 1 less than x is less than or equal to 1%.
Exactly. So again, you would still do 1 minus, I'll just put it back in, binom CDF of what we had above, 50.5 and 19. And so we get 1 minus 0.0595, which comes out to 0.9405. Any questions on that? That part's a little different than when you did the normal distribution. Remember the normal distribution, you had a lower limit and an upper limit, and you could, on the normal CDF, put a lower and upper limit. This you don't have that ability. So you have to do the 1 minus in order to get it. Let's try one more, and then you can try some of the U-try. It says, it is known that 35% of all students fail at least one course over their academic careers, most of them in university. Out of 120 students, what's the probability that at least 50 of them failed at least one course? So, probability that X, they're failing at least 50 of them out of the 120 failed at least one course. So, X is going to be greater than or equal to 50. Because it is the greater than, that's on the right side of the distribution. This is when I have to set up equals 1 minus the complement, that X is less than or equal to, in this case, 49. So I can plug this in as 1 minus binom CDF. What is my number of trials this time? So what's my total number in this case of people?
120.
Yeah, I've got 120. What's the probability that one of them, in this case, fails?
35% all, right?
Yeah, exactly. It's 35%.
Oh, but I thought that's
So that's like 35% of all students fail. So any one student has a 35% chance, exactly. So you have 35% chance that someone fails, and the number of successes, in this case, is 49. So it's cumulative up to 49. And that's why that CDF does this for us.
Wait, why is it 49 again? Is it
Because
because
it's asking for at least 50, which really, if you think about that, at least 50 includes 50.
yeah, it's
So 50 or greater.
Okay.
So
that's why it's minus 1.
yeah, that's why it's 1 minus the
You're
complement.
taking everything what it's and minusing what it's not.
Exactly, you got it. So I plug that in, and you can try that. Yep.
So if it was less than 50, then you wouldn't have to do the 1 minus.
No, exactly. You would directly put in probability that X is less than or equal to 49.
Okay.
Yeah, exactly. That's the tricky part here, is the wording in order to know which one you have to use, 1 minus or not. So in this one, I plug that in and I get 0.92317 ... which comes out to approximately 0.0768. So about a 7.6% or 7.7% chance that at least 50 out of 120 would fail. It used to be that you had to do these things using the Z-score. And that is much more laborious than what you're just doing here. So if you had to go this way, it takes a long time. You have to remember this 0.5 part. It's a bit trickier. I'm not going to make you do that. The chance that you're going to have even this topic maybe in university is probably low unless you're going to take a math degree. So maybe that's the possibility. Maybe, no. So anyway, there are some questions down below. A couple of them are slightly different, but nothing I don't think you can handle, but give them a shot and we'll talk about them. And then the practice questions for this topic are all in the note. So all of there's only 4, and you might get this all done within class.